I think that we can start. Ladies and gentlemen, welcome to this webinar about the recent advances on seismic isolation techniques. And first of all, I want to thank all the participants who want to attend this, I think, a very important webinar. And because of the very important speakers that we will have in the time schedule, starting from, I would say that it is a privilege to have with us Michael Constantinou, which is a distinguished professor at the University at Buffalo. And actually, he has been my key reference in my whole research career about seismic isolation. We know that we all know that he is a pioneer in seismic isolation devices and techniques. So we will have the opportunity to have a big picture of all the research and practical works he dealt with. And then we will have also Professor Virginio Quaglini, who is a professor at the Politecnico di Milano in Italy. And he recently developed a number of very important sliding materials for friction pendulum devices. And he has a very important knowledge for generally based isolation. And finally, we will have actually myself and Professor Alberto Pavese from the University of Pavia and the EUCENTRE Foundation. And we will try to give you a big picture of all the activities, both experimental and numerical activities that we carry out here in Pavia and generally in Italy, according to the commonly adopted devices for seismic protection of both buildings and bridges. And Professor Pavese will also focus on some changes which are actually currently studied for the European standard code for anti-seismic devices. And maybe the committee, which is in charge of these modifications, is trying to actually join what we find out from the research perspectives and what is required in practical applications. So I think that we are in time. I think that we could start so that we are able also to provide some questions and answers times after all the presentations. So again, thank you very much, Professor Constantinou, for being here. And I leave you the floor for your precious presentation.
Well, thank you for inviting me to this seminar. And I have to start by apologizing. I have to cut rather short, I mean, of the 3 hours because I have another commitment, and with this time change, I was expecting to start an hour earlier, but unfortunately, the time change in the United States have made this a problem. So I will make my presentation a little bit shorter and allow some questions at the end within the hour that I have been allotted. So I will start my presentation, and it's a presentation on seismic protective systems, and particularly an overview of the state of the art and state of practice of seismic isolation. So concentrating on seismic isolation is not a general presentation overview of the state of the art and practice of these technologies. You may say it's a biased one because it's based on my experience. That is anyway, the reason I'm making this presentation, I'm not making a presentation to present what others have done. Others in this seminar will make other related presentations. Of the many seismic protective systems you're aware of, I will concentrate only on seismic isolation. And even within that group, I will only talk about a few of those, the most, say, widely used isolation systems. And primarily, these will be sliding isolation systems, particularly the friction pendulum type, and lead rubber bearings, and then viscous devices as they are used within seismic isolation systems. And related to that, I mean, variations of that are used as self-centering devices. The scope of the presentation is a description of the isolation systems and hardware presented through many implementations in bridges, buildings, and the infrastructure. I will emphasize work done at the University at Buffalo, where I come from, and projects in which I was involved. So actually, you're going to see only projects in which I was involved. And the scope is to demonstrate the maturity and technology of the technology and the range of its application. I have many to thank about this work over the years, all these collaborators, students and visitors, postdoctoral fellows and students. I will not make this presentation a detailed one as I proceed, since you have access to this. The presentation has been made available for sharing, so you can go on and read about this. And I would like to have a more general presentation that it includes also a historical introduction and elements, since seismic isolation particularly dates back at least 2,500 years of efforts. And if I were to present that, I will have also mentioned about many others who made contributions that I don't mention in what follows. For example, Professor Kelly and the late Professor Mehin at Berkeley. The younger people now in the United States, I mean, Professor Ryan and Mosqueda, and many others, I mean, worldwide, that I'm not going to mention about in what follows, but I wish I could. A seismic isolation is a method of construction and a technology that is based on introducing flexibility in this isolation system, the result of which is reduction of force transmitted to the structure above and below. It results in reduction of acceleration. We're going to see a couple of examples at the expense of large displacements, and which are concentrated in the isolation system, small structural drift. And I will be talking about displacements that exceed 1 meter. And as a result of that, we need to provide ability sometimes for a significant energy dissipation. Why 1 meter plus displacement capacities? I mean, primarily this has to do with uncertainty in the response, primarily due to record-to-record variability, material properties, modeling accuracy, and all that stuff. And as an example, I provide these two graphs. I mean, assuming that the distribution of the probability of non-exceedance of the displacement of the isolators is normally distributed. I assume that the median is 350 millimeters, and say the displacement capacity is twice that, 700 millimeters. If the dispersion is very low, say 0.3, you have a very low probability of being exceeded, say 1%. But if the dispersion is 0.5, then you have 8% probability of being exceeded. If the dispersion is 0.7, you may have much higher, 16% probability of being exceeded. And depending on the seismic hazard, you may have actually significant dispersion, primarily due to record-to-record variability in particular areas, for instance, South America, Japan, maybe less in the United States, and I don't know about parts of Europe. Now, this it's just a simulation from analyses of An isolated building is the Cathedral Christ the Light in Oakland, California. Is a Catholic church, by the way. I mean, it looks a little bit unusual, but the analysis of the non-isolated on the left and the isolated on the right, same superstructure, you can see the differences in the structural deformations. In this case, displacements are shown with respect to the ground in 3D analyses. Displacements are exaggerated. The isolated structure remains elastic. The non-isolated actually yields. It doesn't collapse, but the glass will have significant problems. It had to remain elastic to be able to fulfill the performance requirements of the owner. I will be talking about lead rubber bearings, friction pendulum bearings, and viscous devices. These are images from actually in our lab in the late 1980s. I will start with showing one application of elastomeric bearings. Of all the applications, this is in a tune mass damper, in which was used for seismic protection, not exactly protection, but reduction of certain response that was problematic on an oil and gas platform in Russia. It consisted of groups of bearings like those shown here in 4 stages. They were 9 bearings connected with a single steel plate over 4 stages, 36 total, 4 of these supporting 100-ton mass. The problem with these is that they are subjected to tension, and I will come back to that. And that was a major issue in the development of these isolators, that they were made maybe a dozen times before they were capable of sustaining tension. And this is from testing in our laboratory some almost 20 years ago. An example of a lead rubber bearing in a hospital in Turkey. This bearing is 1.2 meters in diameter. From that particular project, a force displacement loop, under dynamic conditions and large displacements, these bearings can sustain approximately 50% more displacement than this, which is about 0.5 meter. Say they can go to 750 millimeters before they start having, let's say, problems. Important to note in this is the reduction of strength with the increasing number of cycles as a result of hysteretic heating, a phenomenon that we understand very well now and we can model accurately. Other test results, again, these are from our laboratory for a project many years ago, more than 20 years ago, in the state of New York. And I will point to 2 results on the left. The same bearing at 20 degrees Celsius after 2 days of conditioning, and at minus 26 degrees Celsius after 2 days of conditioning, there is a significant increase in strength, but also stiffness. The increase in the strength is contributed by increasing the strength, the yield strength of lead, as you can see from here, from stress-strain relations of lead. This is pure lead in tension, but also increases in the stiffness of rubber. We understand well this with the changes in the strength of lead, but not that much of rubber, unless we test it. Going to sliding isolators, some images of single friction pendulum bearings at about the time in which they were commercialized in 1988. This is from our lab. I still have this bearing, which is about 200 millimeters square in my office. Actually, I'm just looking at it in front of me. Concave isolators were first introduced in a patent in the United States in 1870. So more than 100 years earlier than this image you see on the screen now. And but they were double concave rolling isolators, not sliding. The largest ever made single friction pendulum isolator is this bearing for the Sakhalin, 3 of the Sakhalin oil and gas platforms in Russia. I mean, typically they look like this. I mean, they are very, very large structures supported on 4 bearings that carry loads from 87 to 103 meganewtons. This is gravity load. Including other effects, they increase to 130 meganewtons. Going to double concave isolators, as I mentioned, double concave rolling isolators were introduced in a patent in 1870, 135 years earlier than the testing that I will mention in these few next slides. This is from testing in our laboratory, and the bearings used in the Auckland Cathedral we saw earlier, the animation were actually double concave with these geometries seen here. Those we tested then had articulation, primarily about concerns with friction being unequal on the 2 sliding surfaces. But since then, when the 2 surfaces have close or almost the same friction, you don't need articulation, and it's not necessary. Testing with equal friction, you get behavior that resembles that of the single friction pendulum bearing. Of course, you have the benefits of increased displacement capacity and, very importantly, division of the velocity to 2 sliding surfaces instead of 1, and therefore you have less heating and less wear and deterioration of properties. When you make friction unequal, you start having adaptive, as we call it, behavior. We have this reduction in unloading force that benefits secondary systems, but other than that, there aren't any other significant benefits than the equal friction case. From testing in the lab, this is 2004 again. This is 3-dimensional. There was a very strong excitation in which the vertical table acceleration exceeded 1g, and the structure actually had global uplift. You cannot see it because it's just a fraction of a millimeter, but you can hear it in the bang bang in the video that had to do with impact during this global. All 4 bearings uplifted at the same time. Going to the triple, a couple of years later, the triple is actually a double within a double. And so you have 4 sliding surfaces, but 3 effective penduli in 5 regimes of operation. You can read about this in the original work of Fens published in 2008. But more advanced models of this in this report, I mean, that is exceptionally more complex modeling than the other, but not necessary for practical applications. This is from testing of one of the isolators. We're going to see a few more images related to this for the San Bernardino courthouse some 12 years ago. And in this case, velocities in the testing were about 1 meter per second, at least in one cycle, the one of the largest amplitude of 1 meter. And these isolators are actually designed, some of them, to accommodate significant uplift. Showing some loops now of these isolators, I wanted to point to these. These are from the San Francisco General Hospital. And if you look at these loops, if you don't know they are from a sliding isolation, you may get confused and believe that these are from an elastomeric isolator. What is important to notice is the effective yield displacement being significant. In this isolator, if you look at it, it's about 60 millimeters. That actually has important effects. I mean, one is in the reduction on the impact on secondary systems. And the other has to do with the recentering capability. They recenter better than those in which they have an abrupt change in the force, like zero yield displacement of the single friction pendulum isolator. In the San Bernardino courthouse, you can see the stiffening behavior of the isolators that are, in this case, displacements exceed 1 meter. This is 1.1 meter approximately. These isolators are subjected to significant uplift. And if you go to this report, which is readily available online, you can see even images in the testing and simulation of the uplift conditions in this report. I will emphasize the significance of testing, not only qualification and prototype, but also production quality control testing. Often in many countries is not conducted. We believe, and actually in the United States is now regulated, that all isolators be tested. We prefer testing to be under dynamic conditions, but it's not always possible. For sliding isolators, at least in the United States, they're always dynamically tested. Very important for that. And it can be done. For example, for hospitals in California, not only is it required to test, but it has to be under continuous inspection. And I have done many of those inspections in which I had to be present for every test. And it can be done. As an example, I mentioned this hospital in Turkey, completed not just 5 years ago, 2,000, more than 2,000 actually, isolators were produced and tested and shipped within a period of 6 months. With sliding isolators, like the lead rubber isolators we've seen, we have significant changes of friction, or the strength, I would say in this case, but we understand that's friction in sliding isolators with heating. And we have understanding of modeling these. And I mean, this report provides an overview of that theory of and validation of that for sliding isolators. The amount of reduction of strength with temperature depends on the materials. But regardless of the materials used, as long as you have friction, you're going to have heating, and those temperatures are significant, hundreds of degrees of Celsius in single friction pendulum bearings. Of course, we see this reduction in both lead rubber bearings and in sliding bearings. We don't see this in high damping rubber bearings, and the reason is that the heating in that case is within the volume of rubber, which is great by comparison to the volume of lead in the case of lead rubber bearings, or the volume of the sliding interface in sliding bearings, which is small because it hits over a small layer at this sliding interface, let's say within the depth of a few molecules. It's important in analysis to account for this variation, which can be significant. We have models to predict that, but typically those are not used in practice. Instead, we test to observe this behavior and determine lower and upper bounds of properties, say strength, for use in analysis. This theory I mentioned about lead rubber bearings is well documented in this. This is one of the papers. This is on verification, and this is from testing of these bearings. There were many actually used in the verification, not just these. And important in this is the prediction of the energy dissipation per cycle as you increase the number of cycles, very well predicted. Of course, we can predict this with thermomechanical analysis, finite element thermomechanical analysis, but for that, one has to have the relationship between the yield strength of lead and temperature, which in our case, in the development of the theory, was based on testing of specimens of lead. Then you can see in this case the effect of temperature on strength, but also on the elongation at break, although that one is not that significant. Now, this theory is based on a complex heat conduction problem, which is difficult to solve except in thermomechanical analysis. What we did in this theory, and you can read about this in this paper here, is that these terms that account for the heat flux through the shim plates and the end plates of the bearing, important in heat conduction, were obtained analytically and used in the theory, in the development of theory, as asymptotic expansions for large and short times. As a result of that, that system of complex heat conduction equations in three-dimensional space were reduced to a single ordinary differential equation for the temperature as a function of time through this equation, which has been now codified in models in OpenSeas and can be used very easily. Important in that is this relationship of strength of lead as a function of temperature. A similar theory was developed much earlier, actually, in 1998 approximately, or originally reported in this report for sliding isolators as they heat. And this is from experiments. These are experiments at small amplitude, and these are from experiments at large amplitude by comparison to the contact area. So if you have a large amplitude, you have intermittent heat flux as you move away from the point of measuring the temperature. But the theory is very good at predicting the temperature increase. It's governed by convolution integral that is easily incorporated in analysis software, and actually has been in OpenSeas for the single friction pendulum isolator, but not for the triple yet, until very recently. So for the one work, the one that I mentioned earlier, a report about the sophisticated model for the triple FP bearing, there is a program, Ripriani, that is provides, computations that account also for a temperature increase and the effect of that on friction, but also provides animation of the motion of the bearings, particularly under uplift conditions. This program was developed, and this theory primarily to look at isolators as they uplift and become likely unstable. But this is an exceptionally difficult program to use and model to incorporate in software like OpenSeas. So a model in OpenSeas that is simpler was needed, and it was just being developed by a student. And the report will soon be available, easily incorporated now in a much simpler way. And this is from a verification of that model. As an example of use of that program, the Ripriani in the prediction of temperature rise in a triple friction pendulum isolator. This was used actually to design an experiment, because this bearing could not be tested at the extreme conditions in this case, was supposed to be tested at 6,500 kip load and displacements of plus minus 30 inches, but it could not, and instead was excuse me, this was the reduced scale bearing that was tested at these conditions, you know, and this experiment was designed so that it emulates the conditions for the full-size bearing that could not be tested, and instead was analyzed in this software, showing some applications of very large displacement capacity isolators. This was several years ago, the Benicio Martinez Bridge in the San Francisco Bay Area, 22 years ago, single friction pendulum isolators. Nowadays, one will have used double concave or triple FP isolators. Going into bridges, and particularly lead rubber bearings. I'm showing this is the Woodrow Wilson Bridge, completed a little bit less than 20 years ago. Is seismically isolated. With the lead rubber bearings that are designed for small displacements. This is in the eastern United States, so seismic displacements are small. There was a concern about the behavior of the bearings under small amplitude motion, and particularly following a significant cumulative travel. In this case, we wanted to look at after about a mile, 1,600 meters of movement that was due to traffic. So when we look at traffic, velocities are small, of the order of 1, 2, 3 millimeters per second, and amplitudes are small, say 1, 2 millimeters. So we tested bearings dynamically, individually, as well as at very low velocities in our own lab. I mean, that was almost 20 years ago. And what we observe is that actually the behavior doesn't change. This is the first 5 cycles of a bearing, very low speed motion. And then after about 1,550 meters of travel, the bearing was left to overnight to cool down. I mean, if it were at all warm, and tested again the next day, and there is insignificant difference. So after a mile of movement, there was very little change in properties. But there were changes finally. If you look at it dynamically at larger amplitude, there is a small difference between before and after, an increase in the strength, but not significant. More importantly, there was significant increase in strength under thermal conditions. The movement here is only 0.15 millimeters per second. So the strength almost doubled, or was more than 50% more. Yeah, about 60, 70% more. So of significance in the use of these bearings in bridge applications. I will talk a little bit about this Bolu viaduct that was under construction, almost completed, when it was hit in November of 1999 by the Bolu earthquake and suffered significant permanent deformations. It utilized an elastoplastic isolation system, like those used significantly, actually, extensively in Italy, and there were a couple of applications, I believe, in the United States. At the time that this was hit by the earthquake, this system was permitted. It's not permitted anymore, at least in the United States, and in some part of the European standards. Well, anyway, I mean, all bearings failed. There were 1,638 flat sliding bearings. There were yielding steel devices that were pulled out of their supports due to excessive displacement demands. And what happened actually with that, it was severely under-designed. The capacity provided was less than half a meter. Actually, it varied between 200 and 500 millimeters. But if you followed the AASHTO specifications applicable at that time of the design, it should have been more than a meter. If this was designed as a 1 meter displacement capacity plus, of course, because this is kind of a median or average demand, it would have been impossible to build it the way it was built. So there was a primary problem in that it was errors in analysis and design, but the isolators were not tested, were not as they were going to be built today, and there was a lack of peer review to catch these errors. Going into these oil and gas platforms that I was involved in 4 of them, these are giant structures, about 100 by 100 meters, give or take, in plan dimensions. 3 of those I'm going to talk about, they are located here off the Sakhalin Island in Russia. The first 2 were completed in 2006. They are not exactly the same, they are nearby each other. And our major contribution in this project was the development of procedures for scaling and testing of seismic isolators. These structures are supported on 4 giant bearings, of which you have seen images earlier. As I showed earlier, the height from the water up there is about 130 meters. Remember, I mentioned about a 4th application of a Tillmans number is in another nearby platform, and the Tillmans number is up here at the top of the derrick. It's only is used there for the protection of the derrick, and particularly its legs that cannot sustain seismic forces related to the seismic hazard of the area. This is a giant structures built partially in Russia, transported to the site, and the top side was constructed in Korea and transported to the site. The loadings in this case, consist of temperatures varying from minus 30 something to plus 30 something degrees Celsius. We have snow and ice accumulation on the platform. We have blast, we have wave, we have seismic. You may think that seismic is very important because they are seismically isolated, but actually it's not. Ice is the most important loading. To give you an idea, the 1 year return period ice load on a single leg is 103 meganewtons. The weight on a single bearing is less than 103 meganewtons. So seismic isolation is not used for the protection of the substructure, or from that point of view, the superstructure, but is used to reduce accelerations in secondary systems that are related to safety. And this is seen in this summary of results for the service level earthquake. So this is the couple of 100-year return period earthquake, and the accelerations at critical locations, particularly equipment. With isolation, they're about half of what they are without isolation, but still are significant, 2G, right? But 2G is better than 4G, but it's not 4G versus 0.4G that we see in some analysis. These are exceptionally complex systems, as well as the isolators are not linear, elastic, and viscous elements that favor, of course, a reduction of accelerations. Testing of these isolators was exceptionally difficult because of the size. So they could not be tested dynamically. And the question is, how do you test these and convince the authorities in Russia to accept them? So the review period for 3 of these platforms took 12 years. And good part of that is the development of a theory for scaling and similarity. So these are the reduced size prototype bearings by comparison to the full size. And how they were tested, there is some information in these 2 references which you can find. Particularly this one explains, I think, well the theory behind that, which is quite sophisticated. And actually, you can find in these elements of performance-based design like those, for example, of FEMA P695, except that it was more than 10 years earlier. Going to applications very quickly now. The very interesting application, first actually retrofit in the United States of the Salt Lake City Hall. I want to point to the isolators, how primitive they look by comparison to those of today's capability to produce isolators. The US Court of Appeals, I mean, a large structure that was retrofitted also with seismic isolation, characteristic of many structures in San Francisco, retrofit of historic structures, architecturally important structures. Important is that you need strengthening, of course, of the structure above. You cannot just put the isolators in there, you know. And this is a fantastic structure. Without isolation, these courts in the interior could not be preserved in this form. This is all Italian marble, by the way, and it was built by Italian artists who came 100 years ago, more than 120 years ago, to build this structure in San Francisco. Now, about hospitals in California, there are several of them that are seismically isolated. Practically all of them now are seismically isolated, new construction. The isolators have very large displacement capacities. So if they are typically nowadays triple friction pendulum isolators, they have capacities that exceed 1 meter. And they also operate under extreme conditions, particularly uplift. This is a list of those. I'm not going to go over this because there is a paper that has information on this. This is the first one, the San Bernardino Hospital built in 1993, is new construction. These are actually high damping rubber bearings and viscous dampers. These are non-linear, actually, viscous dampers. This is an image from testing in our lab, being models with isolators and damping devices. So these are actually low damping rubber bearings, and these are viscous dampers in the isolation system. Some examples: the Apple headquarters in Cupertino, it's a giant structure, 450 plus meters in diameter. There is some triple friction pendulum isolators with a displacement capacity of 1.3 meters. That's all I can say about it because of confidentiality agreements with Apple. Let's look at the smallest, or one of the smallest, the statue of Hermes in the museum, in the Archaeological Museum in Olympia in Greece. These are small displacement capacity isolators placed far away from the pedestal so that there is no rocking. And of course, limited, capacity to move. One reason for that is the statue is in a building that will collapse before the isolators reach this displacement demand. Going into some taller buildings, I wanted to show this one from Japan. And what the Japanese do actually in such cases. And you can see the columns coming down, and then at the ground level, the loads are directed to, in this case, 3 isolators on this side and 3 on the other side, in order to increase the gravity load on the corner isolators and limit uplift. Still, it's impossible to limit it. And if you look at the behavior of this in the transverse direction, the bearings can easily go into tension when the shear is actually very small. So in this case, I will talk about it. It's a very important issue. We looked at tension in elastomeric bearings, and you can find information in this. And but it's basically an unpredictable phenomenon. If they were made, they can sustain tension and cavitate. When they cavitate, they stop resisting and they simply uplift like a sliding isolators. When they cavitate, they look like this, and of course, in this case, they rupture after significant tension. Most often they debond, and that has to do with the quality of construction. We want to limit tension for well-made bearings to less than 1.5 times the shear modulus times the bonded rubber area, which is a rather small force. Now going into implementation with these large isolator displacements, we have issues with utility lines, and I will show some images. This is from the Loma Linda University Medical Center. You can see these large utility lines to accommodate more than 1 meter of displacement. I wanted to briefly show these. These are fluidic self-centering systems. This is a device that resembles, or is based on the same technology as fluid viscous dampers, except that it's built in a way that when you pressurize it, it develops strength. And as the pressure increases, the strength increases. So in the same device, which is small, about 750 millimeters in length, it can move plus minus, tested in this case 50 millimeters, but it can go to 60 millimeters actually, is changing the pressure internally. You can significantly change its behavior. This is not for active control, but it's so easy to adjust this device by comparison to other self-centering systems, let's say based on post-tensioning tendons. Now, these devices are not new. In the United States, they exist for about 40, 50 years now, and there are millions of applications in the military, some of them giant. And I know that manufacturers in Europe, 30 some years ago, they made this and they used in some bridges. So I find it very interesting that we forgot that actually we had technologies that can achieve this self-centering behavior, highly engineered and used, and then we move to develop other ones, ignoring the existing technology. So it's very important for us to go and see what exists there in terms of technology, not always trying to develop new technologies. Looking now at another fancy isolator, the quintuple isolator is a tuple within a tuple within a tuple, or is a triple within a tuple. So it has 5 effective pendula in 9 stages of operation. It's a nightmare to model it, but it was done. And we have models, since it's a triple within a tuple, you can easily model it in a sub 2000, for example. But there is an analytical model that was validated using experiments, and that model then was used for verification of computational models. One bearing, very large bearing tested not long ago. It's a very large bearing. It was the first large full-size bearing tested. The displacements were approaching almost 1.5 meters. It was carrying 2,000 tons of load, and the machine was at its limit when it was tested. I mean, you may have heard things like bolts falling off the machine. I mean, something became loose and fell down. But you realize the complexity of such isolator. It provides for the smooth transition from one stage to the other, including stiffening at very large displacements at the expense of complexity. Imagine now you have 6 sliding surfaces, and no, we don't want to see the video again. 6 sliding surfaces, and the problem is actually knowing the friction force or the coefficient of friction in each one of those 6 surfaces, because in testing, you cannot actually measure that. You can measure the force going through the bearing, but not the force going through each of those sliding interfaces to relate that to the friction force, because what you measure is actually friction force plus restoring force. You have to have a model to be able to, through the model, calibrate, say, and figure out the coefficients of friction from testing. Now, going to this three-dimensional system and isolation system and finishing, I want to point to you in testing of electrical equipment. We had a major project over years to look at protection of electrical equipment. So this is a model of a transformer, rather heavy. This was approaching even about 50 tons on the shake table. And these are triple friction pendulum isolators. If you go and look at the spectra of the motion recorded at this point for several motions, when non-isolated and when isolated. So one of these curves corresponds to non-isolated, and there's a corresponding one for isolated. And we can see the significant reduction in the spectra at all frequencies except the low frequencies here, where is the fundamental, say, frequency or effective frequency of the isolation system. Now, if I go and look in the vertical direction, I don't see any difference, and actually may see some small increase in the spectral accelerations in the vertical direction. So we don't do anything in the vertical direction. We may even amplify a little bit the acceleration as seen in these tests. So we had a project to develop a 3D seismic isolation system. Is for certain weights, I mean, that is used in electrical equipment. And in Western United States, I mean, they're now going with the isolation of electrical transformers. There are, I don't know, maybe approaching 100 of them. All of them, however, use horizontal isolation system, none 3D, because it's not needed except for exceptional cases. So in these cases, this is a difficult isolation system. I mean, difficult system to isolate in 3D because it will rock due to the small distance between the isolators. In a building, you're going to have large plan dimensions, and rocking is not that important. But in this case, there is rocking and it's significant. So in the vertical direction, there are springs. I mean, these are interesting to better understand that, because those springs, when they are compressed and you try to shear them, they may have negative stiffness. Right? I mean, it's a fundamental principle for negative stiffness. So you have to design them in a way that prevents this from twisting due to negative stiffness. And yes, there's a damper also in this case within here, within this system that drives this vertically. And then on top of it, there is a triple friction pendulum isolator. From testing to get an idea of how this behaves, rocks significantly. But has some effect. It's not exactly an isolation system in the vertical direction. It's a relatively stiff, in this case, was 2 Hertz system in prototype scale in the vertical direction, but with high damping, 50% of critical. So it's a highly damped system in the vertical direction. But there are benefits. If I look at spectra, again, at the same control point we've seen earlier, and I see these dashed lines, vertical and 2 horizontal directions. By comparison, at the shake table, there are these. The dashed lines are for the control point up at the top of the structure, and I can see significant reduction of accelerations, spectral accelerations. But at high frequencies, those are the peak accelerations, but everywhere except at the fundamental, again, frequencies of the isolation system. is predictable, the behavior of this. This is entirely in sub 2000. So the dashed lines are analytical, the solid lines are experimental, including vertical displacements. And we have an application. I'm going to finishing up with these few slides. This is the Loma Linda University Medical Center. And when it was, I show images when it was under construction in 2020. And one recent one, it sits on a number of pedestals, 126 with triple friction pendulum isolators on top. These pedestals are supported by spring units and dampers. There are about 1,000 spring units and 1,000 dampers in the vertical direction. There are also dampers in the horizontal direction, and we're going to see images next. And then we have these shear pins that drive the system in the vertical direction and prevent this from twisting. So you need more than one of these at each location. There are approximately 4 at each location. So it looks like this. This is giant. I want to point in this case, the size of the damper, 6.5 meters in length, but also the size of this girder that is almost 1.5 meter in depth to be able to accommodate the large displacement demands and the resulting P delta moments on these girders. So it's not just introducing the isolation system, it's building the structure around it. And images now from construction, you can see the triple friction pendulum isolator here, the pedestal below without the vertical isolation system. This is a damper wrapped here for protection. And a closer look at that, you can see where the pin is going to be inserted. This is from testing of the pins. I was responsible for the inspection of the entire system, as well as the peer review with another engineer. And these pins are approximately 300 millimeters in diameter and about 700 millimeters in length, and they are made of stainless steel, and there are 508 of them. And this is the final image of actually in this year. And everything has been installed, but the springs and the dampers, you can see the pins. The vertical isolation system has not yet received approval, as well as there is significant cost to that. So it may take another 3 years before they find the money, as well as the go through the approval process for the 3D, which started, but it was not completed. The springs eventually, if this is completed, they are going to be installed by GERB, the German company, who are very good at installing springs in structures already built, So this is a structure that is built, and there is a complex process in installing the system, the isolation system, with the springs, since they have to be preloaded. And in summary, I want to mention that there is a long history of developments in seismic isolation. I mentioned about this 2,500-year history that I did not have time to say much about it. It's a mature technology. There is a significant range of applications, from the very little things like that statue in Greece to these giant isolators with 1.5 almost meter in displacement capacities. You can have significant benefits out of this technology. And yet we have many issues to look at. One is procedures for analysis and design to account for lifetime behavior, uncertainty and variability in properties, and uncertainty in seismic excitation. How much capacity should we provide to these isolators to have acceptable performance, but acceptable collapse performance also? The other is modeling this hardware. We're moving in that direction. But when we start looking at heating effects, deterioration of strength and stiffness, there are so many other things we don't fully understand. The other is issues of scaling, similarity, and so on in the testing of isolators as we move to these giant isolators. And still, we don't know fully the effects of time and history of loading and environment on our isolators if we look at lifetimes of 50 plus years. And with this, I conclude my presentation, and I'm open to questions for a few minutes before I yield to, I have a few minutes left, do I?
Yes, Professor. So we thank you very much for your presentation, very, very interesting. And I ask to the audience to write any eventual questions in the chat so that we are able to read and Professor Constantinou can answer. Is there any question?
Shall I, where do I find this? Is it at the bottom?
Yeah, there should be the chat in the Zoom toolbox. But up to now, I cannot see questions.
Yeah, I can't find anything, but I thought maybe.
Yeah, maybe if I read it, I can. I
Oh
can
yeah,
read
if
the
you
question.
read it and.
Yeah, sure. If there is any question, I can surely read the question. It has been a very, very interesting presentation because yeah, you know, these are practical works and real full-scale devices, and I was actually impressed concerning the friction pendulum with 130 meganewtons of vertical load. That is a huge huge device, and maybe there are also some issues about testing such devices. I mean,
Obviously,
yeah,
but
because
to give you an idea of the
yeah.
issue with that, it was the review was done by a Russian committee led by a professor who passed away, unfortunately, just a couple of years ago. Was Professor Drozdov. Professor Drozdov actually was a physicist with a specialization in tribology. And so from the very beginning made it clear that he doubts that it's possible that we will ever be able to convince them to use this device. But as time passed and we proceeded in developing these principles of scaling and similarity, I mean, some of the best works in scaling and similarity, I don't know if you're aware of, are done by Russian scientists, particularly Professor Barenblatt, who is now the Taylor Professor at Cambridge. I'm not sure he still is there, you know, but. And so we based a lot on that work in understanding, and that was impressive for the Russians, you know, that we could understand these things, you know. So eventually they will, they approve that.
Yeah, and I have a question about the quintuple friction pendulum system, and I just wondering if many sliding surfaces may increase the uncertainty in the behavior, for instance, for residual displacements, or just also for force response. What do you think about that?
In terms of residual displacement, it will actually be less, because if you go and look at them, this is if you go and look at this loop now looks like the yield displacement is enormous, so smooth unloading and reloading. So if you look at this, will you know that this is a friction pendulum, a sliding isolator? It looks like a stiffening, a high damping rubber bearing, actually.
Yeah,
and
sure.
In this, particularly this side, which are the experimental, and actually that significantly reduces permanent offset. The problem is more of an uncertainty with the friction values. You know, you have so many to design that to give you some benefit, you know. So you have 6 sliding surfaces. So you need a very experienced manufacturer to produce that bearing. And of course, you need to test it.
Thank you, Professor. There are some questions from the audience. I read the first one. Is it a good idea to provide isolation for residential buildings? If yes, what kind of isolators you recommend, keeping the cost effectiveness?
Well, there are houses that have been isolated for the rich and the famous. Recently, we had a couple of papers related to that in the Bulletin of Earthquake Engineering. And I had a student who did work on what we call a residential isolation system, and actually the examples that were in Turkey. So the student is now a professor in Turkey. Now, there in those papers, there are also there's a review of works of others, going back several years. So if we go to Japan, there are maybe 5,000 residences already isolated, but they came to a stop. There are no more, it seems, than the 5,000. And the reason is that it's really costly to use those isolation systems, And the idea is to use isolation systems that are relatively inexpensive to build. Those we built were made of concrete, and they were rolling concave isolators. The rolling part was made of adiprene reinforced with steel. So if you go and look at that, I mean, there is some effort in that, but the problem is not that we now have isolators that are less costly than, let's say, friction pendulum isolators, or rubber isolators are very difficult to use because there is residential buildings have very low weight. I mean, unless you go to multi-story ones. The problem is the implementation. So
yeah, please.
It costs money to implement it. So don't look at isolation in terms of cost of the isolation system as much as cost of implementing that. You need to do something to put it in the building.
Okay, thank you. There is another one, and the audience asks to briefly describe the vertical dampers which are used within the 3D isolation system.
They are linear viscous dampers. So if you go and look at this image, the dampers, or this is even better, they are linear viscous dampers.
Okay.
So vertically is a simple linear elastic, linear viscous system. Now, the springs have a non-linear behavior as they move to large displacements. You have springs to engage, to stiffen up, like in the friction pendulum isolators, so you don't have very large displacements, but they are springs.
Okay, another question is about the impact forces which are generated due to the uplift in the friction pendulum systems, and the colleague asks for the dynamic amplification factors that we could expect from that impact.
Well, I mean, if you have it depends on what kind of impact you have. So if I go and show something here that I've shown and concentrate on this, this has to do with this, where did I have this Japanese building? I mean, if you have this one here, if I look at this, and I start rocking due to forces in this direction. So this is going to be on two isolators and start rocking. So it's going to be like a rocking system. In that case, it's going to uplift. On the way down, it's going to have significant impact. That's not what is happening in these other applications I described. What you have there is that you have bending of the girders that they uplift and then they come back in. It's predictable actually by analysis, at least in this software we have. I wish I could do an analysis and show you that. But there are increases in the forces, but depends on the type of rocking. You know, if you have this type of rocking, then it's more of a problem than the other type of rocking I mentioned, in which you basically have, or not rocking, uplifting, in which you have individual bearings here and there uplifting. For the Loma Linda University Medical Center, there are some isolators that can uplift several inches, say about, if I say, maybe of the order of not more than 200 millimeters. And the concern there is that the bearings may become disengaged. So, and the question is, how do you design them not to disengage the components and therefore collapse? And that program I mentioned actually allows you to do simulations on the basis of how you configure it to see the effect of that. And very important for that is that rubber boot that there is in the interior of the bearing. Remember, in the testing of some of these bearings that I showed, there was I don't know if I showed that, there is a boot, and that boot is very important in containing the components from disengaging. So this one here, you see this?
Okay, perfect. There is another question about fluid pressurized damper, which have been shown. Could be some issues with the changing of the gas pressure with the temperature?
Well, there is a compensation for that. I mean, in terms of the fluidic force, that is in the most advanced designs is compensated by bimetallic thermostat, so allowing fluid flow adjusted with orifices that adjust the diameter a little bit on the basis of temperature. And that's important actually in heating of these devices also. And then in terms of significant increases or reduction in temperature, if you're talking about, let's say, ranges of, let's say, ambient temperature, say 30 to minus 30 degrees Celsius. Let's say if this were in a bridge outside in Alaska, and you have significant changes in temperature that may affect volume, you may have, in that case, accumulators that adjust for that. But mostly the problem is heating of the devices due to the viscous effects. So the temperatures can increase significantly internally. I can show you images, for example, from testing of devices, viscous devices for primarily bridges, not self-centering, but fluidic devices, viscous dampers, say, in which the exterior of the device is bright hot, you know. This is in infrared images, you know, that we take to see what's the temperature.
Okay,
but it doesn't
question.
have any significant effect on the behavior. Okay. Within the plus minus 15%, we typically, if the manufacturer can do that. Not all manufacturers can do that.
Okay. So last question is regarding the negative stiffness effect that you mentioned for the 3D isolation. Could you briefly elaborate a little bit more about that issue?
Well, I mean, if you take, can you see me? Because I'm showing something.
Yeah, we can see your picture, which is small because you are still sharing your screen. Okay, now it's better.
Okay, now let's say I have a spring and compress it, right? Okay. The springs are like that, and then try to shear it. The spring will extend and push in the direction of displacement. So it's negative stiffness. Every time you have a spring, and you compress it and try to shear it, it develops a force in the direction of displacement, which is negative stiffness. Now, in these springs, as you saw them in that 3D isolation system, there were 4 springs, and the top could twist by comparison to the bottom. And therefore, it could, the negative stiffness created by the compressive force and displacement or tendency to move in shear or in torque could overcome the shear stiffness of the spring itself, because it has shear stiffness approximately the same as the vertical stiffness, by the way, give or take. So you could overcome that. And in order to prevent that from happening, you have to restrain these bearings from twisting. So the need for pins. In the testing on the shake table, we had 1 pin in the middle, so we could not restrain it in torque, in torsion. And to prevent that, we had to increase the shear stiffness of the springs. And how do you increase the shear stiffness of the springs? By reducing the effective length in shear while keeping the effective length in compression. I don't know if I
sure. It was very clear and very interesting.
If I show an image, maybe that one is there. Yes. You know, it's all these manufacturers of these springs, you know, I mean, they know these things, you know, I mean, so it's not if I go and look at this, can you see this?
Yes.
There is something internally coming down. So the spring extends like this, but there is a rod inside that extends over certain length. So if you try to shear it, it bends only, or it shears from here to here. But in compression, it's compressed over this entire length. So the length in shear is shorter than the length in compression. That increases the shear stiffness, that counteracts the negative stiffness.
Perfect. So I guess that there are no further questions from the audience. All the colleagues who have asked the questions, thank you for the explanation and for the answer. And I, again, want to thank you for your precious contribution in this webinar. And we will share these, both the video and your slides of your presentations to the audience so that they can go back and see all the details. And again, thank you very much for this very important opportunity.
Well, thank you very much.
Thank you. So now we can move on to the next speaker, which is Professor Virginio Quaglini from Politecnico di Milano. Virginio, the floor is yours.
Okay, thank you, Marco. First of all, thank you for inviting me to this web seminar. So I will start by sharing my presentation. Just 1 minute. And okay. Okay, do you see my screen?
Yes.
Okay. So the topic of my presentation will be the recentering behavior of curved surface sliders. Curved surface sliders are isolated with curved sliding surfaces, like the friction pendulum, but the friction pendulum system is a registered trademark. So we will talk generally of curved surface sliders. And I will focus on a particular issue that was already mentioned by Professor Constantinou in his presentation, that is the design of the displacement capacity. Okay, we start by speaking of the recentering capability. The recentering capability of an isolation system is a fundamental property because it is related, not only it provides small residual displacements at the end of a ground motion, but also because it is related to the prevention of the accrual of displacements during a sequence of earthquakes. A criterion for the resenting capability of an isolation system is provided in European Code EURES. The criterion requires that the ratio between the design seismic displacement, dm, and the quasi-static residual displacement shall be not less than 0.5. Okay, if we think of an isolation system with a bilinear force hysteretic curve like this one, dm is the maximum displacement during the earthquake, and the rm is the residual displacement which is achieved when the system returns from the maximum displacement towards the origin under quasi-static condition. And this quasi-static residual displacement can be related to the mechanical properties of the isolation system, namely the characteristic strength and the restoring stiffness. Therefore, according to this criterion, the resetting capability depends both on the mechanical properties of the isolation system, which are including DRM, and on the characteristics of the ground motion, which determines the design seismic displacement. For sliding bearings with curved surfaces, like the friction pendulum system, DRM can be expressed as the product of the coefficient of friction times the radius of curvature. And if we think of an exponential dependence of the coefficient of friction on velocity, we will take the coefficient of friction at low velocity as the value to be included in this expression. Okay, but the design seismic displacement, dm, is usually calculated in the analysis, assuming that the isolation system is in its centered position. However, the actual deformation of an isolation system when it is hit by an earthquake the actual deformation can be different from zero, and the system can be affected from an offset displacement during at the beginning of the earthquake. This offset displacement will include different contributions. The non-seismic displacement, D sub G, which is due to the effect of the permanent and the thermal actions, as well as long-term deformation of the superstructures and settlement of the supports. This value can be calculated at the design stage. Another contribution to the offset displacement can be the residual displacement from a previous ground motion, or an offset due to the installation procedure. So usually we calculate dm in an analysis, assuming that the isolation system moves from its center configuration. In case the isolation system is affected from an initial offset that we call D0, this will imply a change in the seismic displacement of a quantity delta dm. And by evoking the principle of conservation of energy, that is, by requiring that these two shaded areas are equal, the change in the seismic displacement delta dm can be related to the offset d0 according to this formula. It is interesting to note that in this formula we can find again dm divided delta drm, that is the parameter that, according to your code, determines the resetting capability. So, isolation system with a good resetting capability will have a ratio dm divided drm quite high, and as a consequence, they are expected to have a low sensitivity to the accrual of the displacement. The accrual of the displacement can affect the maximum displacement during an earthquake, and therefore should be taken into account when we design the displacement capacity of an isolator. The code provides two different formulas for calculating the horizontal displacement capacity, for design the horizontal displacement capacity of an isolator. For systems with good resenting capability, the design displacement shall be not less than the non-seismic displacement due to permanent and thermal actions, plus the seismic displacement multiplied times a reliability factor, gamma IS. Recommended values for this gamma IS are 1.2 for buildings and 1.5 for bridges. For systems with insufficient resenting capability, the Eurocode provides a different formula in which the displacement capacity shall be not less than the non-seismic displacement plus the design seismic displacement multiplied times this reliability factor gamma du times another term which reflects the possible accumulation of residual displacements under a sequence of earthquakes that may occur before the design earthquake. Okay, these provisions were developed more than 20 years ago for accounting for low ductility bilinear systems, and their validity has not been fully proved for isolation systems that are provided with high dissipation capability and have a linear and nonlinear behavior due to the nonlinearities introduced by the friction coefficient, as the curved surface sliders. So, in this presentation, I will investigate how an initial offset may influence the maximum displacement of curved surface sliders during earthquakes. The methods of this investigation will include both experiments and nonlinear time history response analysis. The goals will be to check the viability of the resenting criterion of the Eurocode also for the curved surface sliders and check the displacement capacity required by the Eurocode. So we'll start with the experimental program. I will tell you about some shake table tests that were performed on a steel frame isolated with curved surface sliders. The experimental mock-up consists of a one-story steel frame with 2.5 by 2 meter in plane, a height of 2.9 meter. The mock-up was loaded with a concrete slab on the top and some concrete blocks on at the base level in order to increase the total mass. And at the end, the total mass was 8,200 kilograms. This mock-up can be assumed as representative of a building at 1/3 length scale. By evoking similarity, the following relationship the following scale factors were defined for the main physical quantities. The fundamental period of the mock-up is 0.4 seconds, which corresponds to a period of 0.69 seconds for the full-scale building. The mock-up was isolated by means of 4 curved surface sliders below this red base. Here's the basis. Okay, custom isolators were designed in order to accommodate the gravitational load of the mock-up. These are double curved surface sliders with a rigid slider. Here you can see some pictures. The design parameters were a gravitational load of 20.2 kilonewton, that is 1/4 of the total load of the mock-up, a seismic displacement of plus minus 150 millimeters, and the effective radius was 1,500 millimeters. 3 different sliding pads were included in the experiments, namely lubricated PTFE, a lubricated PTFE compound, and a non-lubricated PTFE compound. The isolation system equipped with the with the three sliding materials was subjected to a dynamic characterization, which provided the following values of coefficient of friction: 3% for lubricated PTFE, 8% for the lubricated PTFE compound, and 12% for the non-lubricated PTFE compound. Okay. And based on these values of coefficient of friction, we calculated the design properties of the cure surface sliders in terms of damped period, damping capacity, characteristic strength, and restoring stiffness. This picture shows the layout of the measuring equipment. We used both a laser displacement transducer to measure the displacement of the mockup and accelerometers to measure accelerations. The seismic input was chosen in accordance to the Italian building code, the NTC 2018, for the life safety limit state of a strategic structure located in Naples and with a nominal life of 100 years. Then 7 natural accelegrams were selected from the European Strong Motion database so that their average spectrum matched the design spectrum over the considered range of periods. And then the records were compressed in time by a factor of squared 3 and scaled to the design PGA. Okay, 3 out of these 7 ground motions are characterized as pulse-like events. Okay, first, the response of the isolated structure to these 2 single inputs was evaluated in terms of maximum and residual displacement. So the isolation system in its centered configuration was subjected to the application of a ground motion. And here are the results. Here we see the relative displacement of the isolated basis of the mockup with respect to the shake table. The max is the maximum displacement, and the rest is the residual displacement at the end of the time history. Okay, here as an example, we see the results for the isolation system with low coefficient of friction, 3%. In light gray, we have the maximum displacement, and in the black, we have the residual displacement. So in this case, we see that we have a very fair recentering capability with a residual displacement on the order of few percent of the maximum displacement. Also, the isolation system with a moderate coefficient of friction, 8%, provided a fair recentering capability. In contrast, when we analyzed the experimental response of the isolation system with non-lubricated pads, 12% friction, the residual displacement was a large part of the maximum displacement, up to 40%. Okay, the result of the test are collected in this panel. On the y-axis, we have the ratio of the residual to the maximum displacement for each time history, and which is plotted against the ratio between maximum displacement and DRM, that is the recentering parameter according to the Eurocode. It is confirmed that the residual displacement decreases with the increase of the ratio of the max divided DRM. However, while for low and medium and moderate friction isolators, the residual displacement is small in comparison to the maximum displacement, this does not occur for isolators with a high friction coefficient. And the residual displacement can be as high as 40% of the maximum displacement, even if the recentering condition of the Eurocode is fulfilled, even if this ratio is higher than 0.5. In a second series of tests, several runs of the same ground motion were applied in sequence to the isolation system. So we started with the isolation system in its center configuration. A first run of ground motion was applied to the sheet table, and we measured the maximum displacement and the residual displacement. Then the isolation system was not recentered, but this residual displacement was left and became the offset for a second run of the same ground motion, and so on. This is not a real condition, but aims at evaluating the response of the isolation system to the same ground motion with different offset displacements. Okay, we have now the results. The white dot represents the maximum displacement, and the black dot the residual displacement. So we see that for the isolation system with either 3% friction coefficient or 8% friction coefficient, there is no accrual. There is a fair recentering capability, as shown in the test with a single ground motion, and there is no accrual. There is no practical accrual of displacement. If we move to the isolation system with 12% friction, we see that there is an accrual, a build-up of displacement, because the residual displacement after a ground motion affects the maximum displacement achieved during the next run of the ground motion. If we now recall the simple analytical relationship that I showed you at the beginning of the presentation between the increase in maximum displacement in the offset, and we plot this relationship, is the dashed red line, we see there is indeed a fair agreement with the experimental results. So we can conclude that the initial offset affects the seismic displacement in accord with the theoretical prediction. Now we report all the experimental data in this panel, considering all the tests, either without or with the initial offset displacement. Low friction isolators and also moderate friction isolators, represented respectively by the cycles and the triangles, comply with the recentering criterion of the EC8, even if they are affected from the initial offset. For high friction isolators, the condition, the recentering criterion of the raw code, does not prevent the occurrence of large residual displacements, as we can see. This is the result of the experimental study. Now, to go more in detail into this issue, we performed a parametric investigation. We consider an isolated structure that was modeled for simplicity as a single degree of freedom system. This isolated structure was subjected to unidirectional ground motions, and the aesthetic behavior of the cursor phase slider was described using a nonlinear friction-bearing element. We disregarded the influence of the axial load on the friction coefficient, but accounted for the effect of velocity in order to reproduce the main nonlinearity introduced by the friction coefficient in the behavior of the friction pendulum. Here are the parameters that were covered by the investigation. 5 different radius of curvature from 2,200 to 5,000 millimeters in order to cover typical radii. For the coefficient of friction, we consider 4 different, let's say, materials characterized by different values of low velocity and high velocity friction coefficient, and 5 different values of the offset displacement, including 0 offset, that is recentering, that is a full centered isolation. Okay, the maximum offset was customized to the friction coefficient and the radius. To perform the parametric investigation, we selected 36 natural ground motion from the PER database. the time history were classified based on the period of the maximum undamped spectral velocity and on the parameter pi, which is related to the pulse behavior of the earthquake. So we have 4 different ranges of periods in order to cover the different fundamental period of the isolation system that were considered in the study, and 3 different ranges for the pulse behavior of the earthquake: non-pulse, pulse-like, and weakly pulse. Okay, this is now let's move to the results of the analysis. First, the system was subjected to the application of a ground motion. The isolation system was in its centered configuration, and we calculated the maximum displacement and the residual displacement. Then an initial offset of an assigned offset was imposed to the isolation system, and the same ground motion time history was applied. In this case, we could calculate the maximum displacement with initial offset, dm, 0, and the residual displacement with offset, dr, 0. Now we report the ratio of the maximum displacement with offset to the maximum displacement without offset as a function of the dm over drm ratio. And what is interesting, so in this we can assess the influence of the offset on the maximum displacement during the earthquake. When the ratio dm divided drm is smaller than 2.5, the influence of the offset may be important, implying either an increase or even a decrease of the maximum displacement with respect to the, let's call, design value that is calculated without offset. When dm divided drm is greater than 2.5, the offset displacement has not a significant effect on the maximum displacement. And due to the large scatter of the numerical data, in the next analysis, we will refer to the 19th percentile of the values. Okay. The curve enveloping the 90% of the experimental data is plotted here in a solid, as a solid red line. And this curve can be expressed as a function of, as a power function of the ratio dm divided drm. So there is a close relation to between the increase in the seismic displacement and the recentering criterion. Okay. We also tried to investigate separately the effect of the radius of curvature of the coefficient of friction and of the pulse chart of the ground motion on the increase of the seismic displacement. There was not any significant effect of the coefficient of friction or the radius of curvature because they are already included in DRM, but we observed that there is a certain influence of the pulse-like character of the ground motion. In particular, when the ratio dm divided drm is smaller than 2.5, there is a high when the isolation system is hit by a pulse-like ground motion. Okay, now let's move to the analysis of the displacement capacity. Now, in these panels, we compare the maximum total displacement calculated by considering body contribution, the non-seismic offset plus the seismic displacement to the design displacement capacity calculated according to the Eurocode. Okay, according to the Eurocode, for system with good recentering capability, the displacement capacity is given by this formula and includes a sort of reliability factor that can be either 1.2 or 1.5. If we account for a 1.2 figure, we found this distribution of dm0 divided d. So this is the ratio of the maximum displacement divided displacement capacity. And it is interesting to observe that when dm divided drm is less than 2.5, for a certain number of analysis, the maximum total displacement exceeded the displacement capacity calculated according to the Eurocode. More in detail, if we move to this panel and look at the effect of the ground motion charter, we see that for the largest number of situations where the design displacement is exceeded, is occurs for pulse cycle events. If we use this different figure for the reliability factor, we found that the displacement capacity is never exceeded. So in conclusion, it looks that the value of 1.2 recommended for buildings in Eurocode is not, maybe not conservative, especially when we are close to defaults where pulse-like events are more likely to occur. In the end, now we look at the influence of the offset displacement on the residual displacement. Okay, here we have the ratio of the residual displacement in presence of the offset to the maximum displacement. The black dotted line envelopes the 90% of the data. The red dotted lines is a formula that was provided by Cardone in 2015 to estimate the residual displacement of an isolation system moving from its centered position. So we see that when dm divided drm is smaller than 2.5, there is a certain gap between the two curves. For large values of this ratio, the residual displacement is not affected from the initial offset, as the two curves perfectly overlap each other. So now, coming to a summary of this presentation, I showed that for curved surface sliders, the recentering criterion dm divided drm not less than 0.5 that is provided in EC8 appears to be little conservative. Based on the result of both experiments and numerical analysis, the criterion delta greater than 2.5 is recommended. This parameter determines not only the recentering behavior, that is the ability to have a small residual displacement, but also governs the ability of the isolator to develop seismic displacement that are not affected from the initial offset. When the parameter is less than 2.5, the influence of the offset displacement under pulse-like events is not fully covered by the reliability factor gamma 1.2. So it is a factor of at least 1.5 seems to be more appropriate also for buildings. When delta is greater than 2.5, the response of the isolator system is insensitive to the offset. So the total displacement can be reliably estimated by a linear superposition of the non-seismic and the seismic displacement. And we are also seeing that the residual displacement can be predicted based on the design seismic displacement of the undeformed system by using the formula by Cardone. Okay, you can find more detail in these papers. which I've already dealt with. I'm the author of this paper, and in which this issue has been already dealt with. Okay, and so I conclude thanking you for your attention, and I'm available for any questions.
Thank you very much, Professor Quaglini, for your pretty interesting presentation. And I ask to the audience to write, as before, some questions that you may have for Professor Quaglini. Yeah, we know that residual displacements are a very big issue to deal with, for instance, with isolation devices with frictional behaviors. And because yeah, the economic part of the project, if we have to recenter all the buildings after a seismic event, should be very, very heavy to investigate. So we need to cover these issues with the knowledge and to investigate something that could actually reduce these residual displacements.
So we also seen that if we have isolators with a high friction, it is very likely that we have a large residual displacement. And if we do not recenter the system after the first earthquake, it may be not protected from a second earthquake, because the displacement induced by the second earthquake can exceed the total capacity.
Yes. Yes, and maybe aftershocks could be of the same intensity of the main shock of a seismic chain. So that is a very big issue to deal with. So I don't see any question from the audience. So maybe there will be okay. There is one. What about the influence of directionality on the sequence of ground motions on residual displacements influence?
Okay, we addressed the effect of the directionality in the numerical analysis and as well in the experimental studies. You can find, okay, I see that there are more details in the paper. We see that the effect, if sorry, I come back to the presentation.
Yeah, you should share your screen again. Yes, okay, perfect, it's work.
Okay. Experiment, we see that in some cases that there can be a decrease of the maximum displacement. As an effect of a small residual displacement. And this can be, the effect of the directionality can be also seen in the fact that in some cases, the maximum displacement of the isolation system with offset is smaller than the maximum displacement within offset of the central system, because this occurs in particular when we have pulse-like events, that we have acceleration history which are characterized by a very large pulse. So in some cases, the residual displacement can be in the opposite direction with respect to the direction of the mean pulse. In that case, the effect of this initial offset is to decrease the maximum displacement. So we can see that in effect there can be either an increase or an increase. There are some figures that, sorry, I didn't have the relevant pictures. I can recommend to refer to this paper where this effect is dealt with, the second paper.
Okay, thank you. I think there is no other questions, but if there are, we can have some extra.
No, yes, sure. I will attend the seminar till the end. So okay, I will.
So we can have some extra time for questions at the end of all presentations. Okay. So thank you again, Professor Quaglini, for your presentation. So now I will provide my contribution to this webinar, and actually the contribution will deal with our experimental campaigns that we carry out at the University of Pavia and the EUCENTRE Foundation in Italy, and they are related to all typologies of the isolation devices, and I will give you a big picture of what we do here. I share my screen. And I start with my presentation. I just briefly introduce myself. I'm Marco Furinghetti. I'm assistant professor of structural engineering at the University of Pavia and the EUCENTRE Foundation. And as I told you, this contribution will deal with the experimental investigation of full-scale isolation devices. And I will go through this outline. I will give you a brief overview of the testing equipment of our laboratory in the EUCENTRE Foundation, which is the bearing tester system, which is a very large equipment which is able to carry out the static and dynamic tests on full-scale isolation devices. We do that for both research purposes, but also for commercial activities and real projects for practitioners. And then I will show some of our research outcomes according to the experimental characterizations for elastomeric bearings with and without lead cores, which is a dissipative addition to the elastomeric bearings. I will show the analysis of the behavior of friction-based devices, which has been actually one of my core research activity. And I will show, especially for friction-based devices, the extra stroke displacement capacity, which is a very recent research topic that I dealt with, which is very interesting because we are actually studying some additional extra displacement capacity when the isolator is subjected to higher displacement demands, higher with respect to the design target displacement. And I will show also results of a hybrid experimental simulation which has been carried out in the laboratory, by considering both the physical substructuring, which consists of a full-scale isolation device, and a numerical substructure, which is actually a numerical model, a simplified numerical model of a building base isolated through this typology of devices. So this is an overview of the bearing tester system at the EUCENTRE Foundation in Italy. There is actually a reaction arch which is actually able to provide the reaction force with respect to the vertical application of forces. And then there are actuators which leads the isolator to displace in horizontal directions. And actually in the picture, you can see a special setup which has been considered for some testing campaign research. And this particular testing setup is able to perform tests in both directions in the horizontal plane, so that there also bidirectional paths can be applied and investigated through the application of motions, bidirectional motions to the isolation devices. And this testing equipment is installed within the Shake Lab in the EUCENTRE Foundation. These are some of the most important technical details of the equipment. And you can see the maximum displacement which can be applied for both the longitudinal and the transverse directions, and also for the vertical one. And the vertical one is actually very important because, for instance, when we test some devices, some friction pendulum devices, we know that there is also vertical motion due to the curved shape of the sliding surfaces. So we need to have a large allowance of vertical displacements in order to actually provide the realistic motion of the device. We have also a large allowance of maximum velocity up to 2 meters per second for the longitudinal direction, which is actually the main direction which is used for all the purposes, both commercial and research. And then we have a very large allowance of vertical force, which can reach up to 40 meganewtons in the vertical direction, plus and minus 10 meganewtons for dynamic excitations, and also a very large allowance for the longitudinal force, which can reach 2000 kilonewtons. And I just start with some examples of the outcomes of our testing campaigns. And actually, we start from elastomeric bearings. And we know that such bearings can provide a very low stiffness layer for instance, an isolated building, or also for bridges, generally for a structural system. And the large displacement demands can actually be limited thanks to a certain and limited also energy dissipation capacity. We can distinguish between low damping rubber bearings and high damping rubber bearings with equivalent viscous damping equal to 5 to 10% for the low damping, and 10 to 15, 20% for the high damping rubber bearings. There are several compounds, elastomeric compounds now available with even larger dissipation capacities. And I just want to show a video of a dynamic test of a particular elastomeric bearing, which was a fiber reinforced elastomeric bearing with actually a particular behavior. So you can see that the hysteretic loop can be easily represented by a stiffness, a linear stiffness with an equivalent viscous damping constant with respect to the displacement. There is a little bit of degradation of the mechanical properties of the device, as we can notice from the graphical results. A decreasing value of the stiffness, of the second stiffness at maximum displacement, and there is also very interesting behavior of the rolling rolling motion during deformation. So what we did in our laboratory is to actually analyze the whole database of the tests carried out for elastomeric bearings, both the low damping and the high damping, and by analyzing 1,400 dynamic tests in order to actually experimentally assess the second stiffness at maximum displacement, and in order to compare the target value of shear modulus of the rubber with an experimental evaluation of such parameter. And this is actually what we found out. This is a distribution of the parameter of the experimental parameter divided by the target one. And we can notice that, okay, we can approximate that behavior by a Gaussian a normal distribution. And we can see that the mean of such a distribution is not equal to 1, but it is something like 14%. 1.14, so it is 14% higher than 1, which means that the experimental shear modulus of the elastomeric bearings is averagely, we can say averagely higher than the target one, and slightly higher because we have a 14% more than the target value, but generally this is the result for full-scale devices. So actually, by considering the dynamic tests carried out on full-scale devices for both research and commercial purposes. So we try to do the same study also for the elastomeric bearings equipped with the lead core. And so these are similar devices because the rubber portion of the bearing provide a significantly low stiffness for the isolation layer, so that we can provide a period shift to to the overall structural system. But the lead core provides a significantly higher dissipation capacity to the overall device, so that the equivalent viscous damping can achieve values up to 25–30%. And actually, what we did is again to consider the whole database at the EUCENTRE laboratory, and we consider 900 dynamic tests of full-scale devices for both research and commercial purposes. And this is a distribution for the yielding displacement of the lead core divided by the total height of the device. This is a sort of the yielding strain for the lead core. What we can find out is that the dispersion is very wide, but we can also notice that the peak value of the normalized frequency is related to 3% approximately, 3% of yielding strain for the lead core. This should be a very important parameter for a very get started design procedure, and maybe when designers are asked to define the characteristics of isolation devices. And we did also the same for the yielding stress of the lead core, and the variation is a little bit more limited. And we can notice that the peak value is related to 10 to 11 megapascals of yielding stress. And we also provided a study, a statistical study for this ratio, the left-hand side ratio, which is the lead core diameter in a plan view over the total height of the device. This is a geometrical parameter. This is not a mechanical parameter, but it could be useful for a very initial design of lead rubber bearings. And actually, all this information can be implemented for very fast design rules for isolation systems, and a research article will come out for very soon on the topic. Actually, I just got minor revisions in the process, so I will inform you if you are interested in as the article will be published. And also the results are also all helpful for the definition of bound analysis, which are generally ruled by any standard codes worldwide. So in order to consider that mechanical properties of isolation devices are not deterministic values, but on the other hand, they are actually random variables. So we should note that in our design that there is a certain variability for such properties, and maybe we can perform bound analysis in order to maximize displacement for the isolation system, and maybe to maximize also internal forces for the superstructure, for instance, for both bridges and buildings. And now let's start talking about behavior of friction-based devices. This bearing can actually provide a large dissipation capacity due to the friction motion at the sliding interfaces. We can see all the components of the isolation. Professor Constantinou is a pioneer of this technology and has shown very interesting applications on that, and the huge devices. Actually, this is actually a rendering of a prototype that we have designed and tested, and that we show later on the results of such a testing campaign. This is an example of a dynamic test of such a prototype. You can see the commonly known behavior of a longitudinal test, and it is actually the vertical unloading branch for the force displacement loops, which is directly related to the frictional behavior, and then the post-yielding, let's say, stiffness is related to the recentering capability of the device itself, which is directly provided by the curved shape of the spherical shape of the sliding surfaces. And we can also notice a very important behavior that has been mentioned also by Professor Constantinou, which is the degradation of the friction coefficient as the motion goes by. This has been a key issue for our research activities in order to actually try to model easily, very easily, such a behavior within analytical models, which can be also easily implemented from both perspectives of fast computations and computer computations, so within softwares. And this is actually an example of such a model. We tried to express such degradation of the frictional properties of the device as a function of the dissipated energy, which gains during motion and during a seismic event. And the dissipated energy is computed actually for the for the isolation level. And this is a meaningful correlation, which looks meaningful actually, because the decay is due to the heating phenomena which occur at the sliding interfaces. So the energy dissipated during the motion may reflect that such phenomena. And we can see that these actually for this device, but generally we can say this phenomenon it can be easily modeled and represented by a decay, an exponential decay, as you can see in the slide. And we were also able, with the special setup I shown before, to apply bidirectional orbits. And actually, I'm showing the curvilinear cloverleaf orbit, which is actually ruled by the European standard code, the EN 15129. And actually, we are also able to provide bidirectional cloverleaf orbits with a constant tangent velocity during the whole duration of the test, so that these are some details, mathematical details, in order to compute a new time vector which provides actually the constant tangent velocity for all the instance of the cloverleaf orbit. And this can be also done for not only for the cloverleaf, but also for any kind of bidirectional path for the device. We can see also the H-shape, the spiral, and the circle orbits. And you can notice at the bottom part of the slide, we have the tangent velocity modulus with respect to time, and it is actually constant, but the location of the starting and ending loop of the tests. And these are actually some important results that we obtained in the very first investigation of the cyclic behavior, which is actually the degradation of the frictional properties with respect to the dissipated energy. And we can see that with respect to the unidirectional decay curve, which is the black dashed line, we have overlapped the experimental decay curve for all the orbits that we have investigated. And we can see that the trend is averagely the same, but we can also notice that it is slightly increased with respect to the unidirectional case, which is the black one. And this may be addressed to the heating phenomena which occur at the sliding interfaces, because when we apply a unidirectional motion, the internal slider of a friction isolator actually is subjected to motion in always at the same locations. So the heating flux is which originates at the sliding interfaces is much higher with respect to the one which can be obtained in bidirectional motions, where new portions of the devices are actually investigated during motion. And in order to consider an average friction coefficient per cycle as the one which is ruled for unidirectional motions by the standard code, the European one, we did exactly the same definition, which is this one, but instead of 4D max, which is the commonly adopted formula in the European standard code, we consider DC total, which is D stands for displacement and C stands for cumulative. So it is actually the length of the path which the device is subjected to, and we can see the expression, the mathematical expression for that parameter for all these shapes. And actually, these average values per cycle are actually in agreement with the unidirectional curve, exception made for the circle orbit, which is actually a very particular case. So then, in order to widen the investigation of such effect, the two individual devices, full-scale devices, have been realized. Actually, a flat slider and a double concave surface slider isolator. So this is the flat slider, the prototype. You can see that there is just a flat sliding surface, which is a stainless steel surface with a roughness index of RA 0.2. And there is just a slider, a flat slider with different sizes in diameters, and we show later on. We have also investigated some sort of size effect for the friction properties. And exactly with the same diameters, we have designed also the double concave surface slider isolator. And these are actually what I mentioned, the different diameters for the flat slider. And we were also able to consider not only 260 millimeters for the curved isolator, but also exactly the same values related to the flat slider. And actually, together with Professor Quaglini and Dr. Dubini from Politecnico of Milan, we have equipped our devices with innovative sliding materials, which are PTFE-based materials with solid lubricate and filled with the bronze fibers for material A and carbon fibers for material B. So we were able to apply both the radial and bidirectional motions, and for the bidirectional one, we applied the cloverleaf orbits performed as several combinations in this research campaign of the sliding velocity and vertical load, and also for earthquake simulations. This is the main difference between the ordinary, let's say, cloverleaf orbit and the constant tangent velocity orbit. You see that the duration is shorter, and that the modulus of the tangent velocity actually in the ordinary equation, which are actually implemented in the European standard code, it is bounded between during motion. It is bounded between 50% and 100% of the maximum of the peak value during the test. Whereas with the sampling procedure that I've shown before, we are able to apply exactly 100% of the peak value for the whole duration of the test. And this is an example of a curved device subjected to a constant tangent velocity cloverleaf orbit. So this is a bidirectional test. We can see in the video and now we start that both the components, the longitudinal and the transverse, and exactly the same behavior for the hysteretic loops. And you will notice in the left bottom part of the video, actually the recordings, the video recordings of the test of the isolator, and you will notice that the velocity of the device does not change during time after the starting of the cloverleaf orbit. So you can see that there is no changing in the modulus of the sliding velocity, and that we can notice also the highly nonlinear hysteretic loops for both the directions of motions. And these results have been used in order to compute also the average friction coefficient per cycle that I've shown before. And these are actually results as in terms of friction coefficient with respect to contact pressure. So this with respect to the applied vertical load, and for different values of velocities, of peak velocities, by comparing different diameters of the sliding pads. So this was just to carry out a comparison of the size effect of the internal diameter of the sliding material with respect to the friction coefficient. And we can see that the overall behavior is very similar to all the implemented diameters, also for higher velocities, and for all the pressures that have been applied, which siems to suggest that maybe the size effect is negligible, actually, for the size that we have investigated, at least. Then another very important study that we carried out was the comparison between the composition force of the curved device in terms of flat frictional force and a numerical restoring force of the device. Actually, we were able to compare the responses because at the flat device we have applied a testing protocol which have actually half of the displacement demand with respect to the curved device, since both the sliding surfaces have the same radius of curvature. And this is the video which shows actually the time series of longitudinal and transverse forces. And we have also the recording videos of the test, and at the left part we have the curved device, and the right part the flat slider. You will notice that the motion of the flat slider is pretty much shorter, I mean, with respect to the curved one, just because we applied it a testing protocol with hard peak displacements. And this is the video. For the whole duration of the test, the composition of the force, so by summing up the flat slider response to a numerical restoring force, we can have actually a fairly good estimation of the curved device response, which is a very important information, because when maybe we have to deal with very large devices, curved devices with very large force demands, and maybe laboratories are not able to provide dynamic tests on them. So maybe we are able to estimate the behavior of the curved slider just by considering the flat sliding material, so with no actually spherical surfaces, and by modeling numerically the restoring force. That could be a very interesting development for the testing techniques. And these are also the numerical results for a given pressure and for increasing vertical load for the same sliding velocities. And actually, we did exactly the same that I mentioned before, the definition of the bidirectional cycle. And according to the bidirectional cloverleaf orbit, we can define as a cycle the set of two consecutive lobes, since from the zero displaced configuration, we reach the peak value twice. So this is very comparable to the unidirectional motion, and there is also very similar equation. This is the one ruled by the standard code EN 15129. We have 4 times the max, where the max is the peak value, just because in a sinusoidal waveform we reach the peak value 4 times. But concerning the bidirectional cloverleaf orbit, we can notice that this value becomes 4.844 Dmax, because this is actually the length of the total path of 2 consecutive lobes. So that is the total cumulative displacement per cycle. And these are results in terms of, let's say, average friction coefficient per cycle with respect to the dissipated energy, so the cyclic effect. We can notice the common behavior that we have described before. And this is a very important outcomes that we got in the experimental campaign. This is a comparison between the decay curves of the friction coefficient between radial 1D and bidirectional 2D motions, we can see that this is the lowest, the lowest applied vertical load. And we can see that there is a non-negligible difference, and that this was addressed to the different heating phenomena which occur during 1D rather than 2D motions. And those differences become negligible as the vertical load is increased. You can see that this is the highest vertical load that we applied to our devices. There is a very small difference. And these are results also concerning the wear evidence for the sliding paths. We have much more wear in flat slider paths with respect to the curved ones, just because maybe there is a certain effect, a confinement effect for the sliding material, which is not available when we implement the sliding material into a flat slider, but it could be also provided when we use a double concave surface slider device, generally a curved slider. And finally, I want to conclude by showing a very important study that we are considering, and it is actually under consideration for the revision of the standard code, European standard code, which is the extra stroke displacement capacity. So if we are able actually to apply displacements higher than the target value, the design value. And this was studied for this prototype, which has actually the stainless steel sliding surface, which is installed within a counterbore gap. And these are the displaced configurations of the device. We can notice that there is the extra stroke displacement, and there is actually a geometrical ultimate displacement where we have actually we have a mechanism here, because after that value of displacement, we can no longer have the transfer of vertical load from the superstructure to the foundations. And we have noticed also that the distribution of the vertical stresses induced by the vertical load, the applied vertical load, can significantly influence the pressure at the sliding interfaces, because we have to distinguish between the covered area, which can be considered where when we have the height of the internal slider, which is significant, and the overlap with respect to the overlapped area, which is shorter, and actually if it is smaller, the pressure gains much faster. And this overlapped area should be considered if the height of the internal slider is small. And these are results by applying displacements higher than the target value. You can see that we can notice just an increase of the friction coefficient, which is also limited with respect to the ordinary value in the ordinary stroke. And actually with no significant difference in the restoring behavior. This tangent line is actually approximately parallel with respect to the extra stroke behavior. And this is actually what we developed, an analytical model which just provides an increase of the friction coefficient as the target displacement is overcome. And these are results in comparison to the numerical model just by looking at the normalized frictional force of the devices. So we tried to consider also an hybrid experimental simulation, which actually considers an accelerogram as an input for the dynamic system, and the dynamic system is substantially the numerical substructure, which provides a displacement output, which becomes the input value for the bearing tester system, which actually tests the physical device, which is the physical substructure, and the output of the force response of the device represents the input of the force of the force response of the isolation system in the next iteration of the dynamic system, and the stepwise interaction between the numerical and the physical substructures. This provides the final solution of the system. For this particular hybrid simulation, we considered a 3-story reinforced concrete building as a physical numerical substructure that we have to invert these titles. And actually, we modeled that building by means of a spatial condensation procedure, so through lumped mass oscillator. And this is actually the physical device we tested, which is actually a full-scale device. And this is a video which shows actually both the displacement path and the hysteretic loops. The hybrid simulation was carried out with a time scale equal to 8, so it was the time scale was shorter, and actually was lower actually, and the vertical load applied was 1,500 kilonewtons. But you will see the video which has been sped up to real time, and we will notice in the force displacement behavior that there will be an increase of the friction coefficient as you see as the design displacement is overcome. And in this test, we were able to notice the overcome of the friction of the design displacement in 3 times, so that we can also notice that the friction coefficient after the second overstroke behavior it decreases, just because there is a huge damage, as you can see in the sliding material, because there are portions which are actually cut at the sliding interfaces. You can see in the video, this is the last time, you can see that there are no longer all the portions available in the sliding materials, so that if you have less material, directly we have higher pressures, and if you have higher pressures, we have a decreasing value of the friction coefficient. So these are references you may be interested in, which are actually showing all the results of our testing campaigns on the topic. And I want to thank you for your attention, and I'm ready to answer to questions from the audience if there are. And maybe and then we will have the last contributions. So there is a question. Can the vertical load be changed dynamically along with the horizontal load during the isolation test? Yes, we can do that. And actually, we did some tests with both the vertical load varying with a sinusoidal waveform, but we were also able to perform some, earthquake simulations by varying the vertical load as a function of the vertical ground motion recording. So yes, it is possible to vary during test the vertical load with also not only with a sinusoidal waveform, but also with a given numerical function, which is actually loaded as a signal in the testing equipment in order to perform the test. The only issue is to be sure not to apply tension to the device, because we are not able to apply tension to the device with an ordinary setup. Maybe we could do that, but we have to study a particular setup to implement. Thank you for the question. If there are other questions from the audience, or maybe we can also have some extra time at the end of all presentations. So I thank you again for the attention, and I switch to the last presentation, which is the presentation of Professor Pavese.
Thank you. My presentation will be on testing strategies for anti-seismic devices in European codes. In the present time, and EN 15129, the reference code for design of isolation structure are currently under revision phase, and the update will concern for the specific subject of the isolation, the implementation of a new procedure for designing the isolation structure and also for testing of the isolation devices. The study that I would like to present here are focused in the comparison between the testing requirement that will be are currently in force in the European code, and the results of a nonlinear thermistor analysis that has been performed on two reinforced concrete buildings that have been used recently for the development of a research project funded by the Italian Civil Protection Agency. Each building, the reason for this is to try to understand if the testing requirements are able to cover all the real situation that may happen in a real building when subject to real event. Each building has been designed for using for a different type of isolator, low damping and high damping rubber bearing, and also lead rubber bearing, and again for curved surface slider, well-known friction paint. The results that are presented here are limited only to HDRB and curved surface slicer, of course, for reason of time. These are the building that have been used for this study. The building are a reinforced concrete structure. In the first case, we have a building with a basement plus 3 floors above ground, with a central stair, and there are, of course, a layer with wall, and the other part is a reinforced concrete frame. And the second one is a pure reinforced concrete frame. In the first case is a 4th floor. The second case is a 6th floor with different height, 15 meter and about 18 meter in the second case. Both of them are sited in high seismicity area in Italy, as is displayed in the Italian map here. The isolator have been designed with using the Italian code, which in many points is very similar to Eurocode 8, specifically for what concern for instance, the choice of the action that has to be used for the design. In this case, we are here the response spectrum for the Italian code for the first building, and for the second building is the black line, and the colored line are the spectra of a natural event that has been used for the nonlinear time history analysis. The green line here and here are defined the range of compatibility that are stated in the code. This, of course, for building 1 and building 2. So going to the some results here are presented for the case of the high damping rubber bearing, is the comparison of the deformation, the shear deformation that it's has been recorded during the event. The event chosen R7 as required in the code. So here are presented the 7 event plus the average value, both in a positive and negative direction. Some of them are below and some other are above and overcome the value of 100%. This for building 1 and for building 2, but generally speaking, I would say that the average value is in the range of 100%. So the requirement of the code is to test for using free full cycle at 5, 10, 20, 50, and 10% and 100%, I'm sorry, of the deformation, the shear deformation, which is in some way, let's say, compatible with what happened. The number of cycles prescribed are free. Here there are some cases in which, for instance, for some the isolator, there are a lower value, and for there are a bigger value. So the number of full cycle does not match exactly what happened in the real case, or at least in the simulation. This is also true for the case of the building number 2, and these are on the other side. These are the comparison of the frequency that are required by the code for the performing the cycling test at 100% of deformation. Frequency are 0.1, 0.5, and 2 Hertz. Here are the monitoring of the frequency corresponding to the maximum displacement that have been, as I said, recorded during the event. This is the minimum frequency, this is the maximum frequency for the 2 buildings. The range of variation is very similar for both. It's between 0.25, 0.83 Hertz, which is compared to the value that are reported here, are at least very are far from the upper limit, which is 2 Hertz. Another requirement, another test that is required for this kind of isolator is the execution of the 10 cycle test at 100% deformation, and it's again comparing the 2 previous figure corresponding or 2 specific joint. These are more specific the joint that are placed in the corner of the building, which might be considered as the worst position for what concern also the rotation given to the, I mean, some irregularities that might happen in the building. But it's clearly seen that the number of cycles used in this test is very far from it. Also at 100% of the maximum deformation is very far from what it really happened in the simulation. This is a figure that shown the value of the maximum of let's say the variation of displacement in red, and the velocity in blue, and in black it's the variation of the vertical load, the load applied to the isolator. These are the position of the maximum value of load, and the maximum load, maximum displacement, and the maximum velocity. And this for the case of building 1 and building 2. And this is to prove that the execution of the test of at the maximum displacement using the maximum load might be too severe compared to what happened in the real cases. Here also a table, particularly I would like you to focus on this table, in which there is the range of variation for the 7 accelerogram of the maximum vertical load compared to the testing vertical load given in the code. So we have variation that are from 2 to 3 times more or less the value of the load that is prescribed. And for the minimum value, there are cases in which we might go also in attraction in some cases, but there is nothing that is prescribed in the code about this condition. As an additional, let's say, parameter of comparison, I have also here the mechanical work fulfilled during the seismic shaking compared to the mechanical work fulfilled during the free cycle, the test cycle, 100% of the formation testing lab. So in the first case, they are, I would say, much similar. In the second case, are very different. This is another way to, let's say, evaluate the efficiencies of this kind of test. For curve surface slider, consideration are similar. I don't have time to go in too much detail on that. Here, for building 1 and building 2, isolated with the curve surface slider, are given the variation of the real velocity compared to the testing velocity, and the displacement obtained during the nonlinear time history analysis compared to the value that is being used should be used for testing. Of course, I'm referring to IT test, which is the most demanding kind of test that is prescribed in the code. You may see that there are regular, let's say, regular situation in which the value prescribed in the code are overcome. As you may see here, both for building 1 and building 2, even if the average value is close to 100%. So in the case of displacement, this means that there might be extra stroke demanding. Again, also in this case, we have a situation in which maximum load and maximum displacement are not synchronized, so which is not happening in the test. And in these cases, we have also the variation of the maximum load. I would like to underline this, and this, which are the situation in which there are extra stroke, A1, A3, and A6. This is the percentage of Dmax compared to the testing displacement, and there is also here value of the Nmax, so the maximum vertical load that is applied to the isolator. So recently, this has been considered, but this value, of course, puts some light on a possible re-examination of this situation. So, try to draw some conclusion on this. We might see that at least for the 2 buildings that has been used for this simulation, of course, these are not general conclusion, because it's almost impossible to give a conclusion with only 2 buildings. But certainly in this case, some critical points have been let's say, recorded when consider the frequency of application of load and displacement, the number of the cycle compared to the real number of cycle, and the axial load used for the test or the displacement target. This is particularly critical for the case of the friction pendulum. An alternative approach, it's very difficult, of course, to have a testing protocol in which there are specific combination of velocity displacement and axial load that could, let's say, include all the situation that might happen in the real case. A possible alternative procedure could be the use of free value of pressure, free value of velocity, and free value of displacement, and combining them to try to prepare for each couple of these surfaces. I mean, perform tests with, I mean, combining pressure and velocity, pressure and displacement, and velocity and displacement, and whatever, and using using let's say the experimental value to prepare some interpolating surface, which are let's say give the possibility also to let's say define the value for specific situation that are not included in the testing procedure. Another possible say subject is the one that has been indicated during the presentation of the response of the displacement, which are for the overcome of the shear deformation, or generally speaking, of the lateral displacement of the isolator. This is an issue. I mean, for the case of the rubber bearing, this implies an higher shear deformation. Many tests have already demonstrated that the isolator, the current isolator, the isolator that they currently used, are able to sustain even much higher deformation under specific condition. In the case of a curved surface slide, this might be more critical. If the approach is to put the external ring, as is prescribed in some code, the idea could be that we might have a situation in which we can, for instance, have damage of the external ring, as in the case is displayed here. If there is no ring, but is allowed the extra stroke as it is prescribed in the European code, this might be the results of the damage in the sliding surfaces applied, and the sliding surfaces applied used in the curved surface slider with scratches, very deep scratches in the external part. This issue of the testing of the extra stroke is in some way to be considered as a possible addition in the testing protocol. This is an example of the testing of the test performed on the device using the hybrid simulation, which the technique that combines experimental test and numerical model. And you may see here the typical response curve of the isolator with these two big area at the end, which demonstrated the presence of an higher friction on the external part of the isolator. But since, as we have seen that in a building, a real building, there might be extra stroke, and even if in some cases, for some code, for instance, 9 hour in the European code, there is a safety coefficient 1.2. Of course, in the nonlinear time instance simulation, we have seen that there might be a much higher value of extra stroke. This kind of test might be considered as a possible additional test to prove the let's say the behavior of the building in this specific condition. Finally, I would like to underline the fact that in codes, in general speaking, there are no specific recommendation concerning the accuracy that is required for the execution of the test. When performing tests, there are different situations, some typical situation of testing rig layout. And for this typical situation, there are a source of uncertainties, essentially related to friction and additional inertial forces that, of course, are added to the real force of the isolator, both on a horizontal and vertical direction. And this might have, some relevance in the definition of some parameters that are derived from these forces and displacement. For instance, here there's a very simple example of what happened, for instance, in the case of the calculation of the damping coefficient. This was my last slide. I thank you very much, and of course available for any question you may have here.
Thank you very much, Professor Pavese, and you can join for any questions from the audience. Again, if the audience has some question, can directly write in the chat. Okay, let us see if there is any question. Just a second. Okay, Professor Pavese, can you hear us?
Yes, I do.
Yeah, okay, we can also hear you. Okay, there are some questions. Maybe you can also read questions in the chat. You should be able to. Otherwise, I will read.
You better read for
yeah, sure.
Everybody.
Okay. There is one of the audience, one colleague who says, thank you so much for this kind of presentation. I'm wondering if we can use the isolator device in the mega subcontrol structure system between the mega columns and substructure, or only we do use it in the foundations.
I don't see any reason for, limited the use of the isolation. So in any case, when you have to decouple big mass with the foundation is fine. I think that it's only matter of having the right kind of isolator, meaning the right technology, and of course the right design for what concern displacement capacity and force capacity. But I don't see any reason to say no. Yes.
Yeah, there are also recent research studies about the interstory isolation systems. So there could be also isolation systems at a certain height of the building, not only at the base.
Yes, sure. Well, this is a very typical approach that has been used, particularly in China and South Korea. There are many applications of this kind.
Yeah, there is another questions. Very interesting study and comparison. The colleague, thank you for your presentation. And the question is, what is the status of an update to EN 15129?
Oh, well, that's a very good question. I know that in the floor there are other colleagues that work with me in the WG, so the working group that is dealing with the revision of the code. The situation is that at this moment is not very clear what are the rules for the modification of the code. We have completed the revision of one clause, so one chapter of the code, and we have done the submission to the European Community for preliminary validation. If the answer will be positive, as we hope, we will start with the revision of all the clauses in the norm. And my guess is that the new version of the norm will not be ready for publication before 1 year, 1.5 years. So it means that will be hopefully published in about, I would say, optimistically 2 years, but it's more convenient to say 3 years. It's just a guess, of course. It's just my guess.
Okay, thank you. I think there is no further question. Okay. Yeah, I think this is the case. So Professor Pavese, thank you very much for your presentation. Very, very interesting and up to date. And for sure, if there is any further questions also after this webinar, please you can email us to our email addresses so that we can try to share our knowledge with respect to the isolation techniques topics. And I think that if there is no other question for also the other speakers, I think we can end up with this webinar. I want to thank you all for attending this important occasion to share actually our expertise in the field of seismic isolation. We have recorded these events so that we will be able to share also the video recording. I will do it through my YouTube channel, where I will give you the connection link with through an email. And obviously, we are always open for cooperations for both the commercial and surely research activities. We can discuss about cooperations and research cooperations. So thank you all the participants. Thank you, Professor Quaglini. I see that you are still online. I want to thank you again, Professor Constantinou, for attending this webinar, for providing a very useful contribution. Thank you again, and see you the next event.